Look up at the night sky on a clear evening, and you might feel a sense of wonder, maybe even peace. Those twinkling stars seem almost friendly, like distant lighthouses guiding us through the cosmic ocean. But that sense of calm is an illusion, a trick of distance and atmosphere. The reality of space is something altogether different. Something that would fundamentally shatter our sense of security if we truly understood it. Space isn't just empty or cold or dark. Space is actively, relentlessly hostile to everything we are, and everything we need to survive. It's a realm so fundamentally alien to human existence that every single second spent there is a defiance of nature itself. Let's start with something basic. Something we take for granted every moment of our lives. Air. On Earth, we're surrounded by it, sustained by it, barely even conscious of it, unless the wind picks up or we hold our breath for too long. But in space, there is no air. Not a little bit of air, not thin air, but absolutely nothing. The vacuum of space is more complete than anything we can create on Earth. Within that void, your body would become your worst enemy. If you were suddenly exposed to the vacuum of space, you wouldn't explode like in the movies. But what would happen is arguably worse. The air in your lungs would expand rapidly, and if you tried to hold your breath, your lungs could rupture. The moisture on your tongue, in your eyes, on your skin, would begin to boil. Not because space is hot, but because in the absence of atmospheric pressure, water boils at body temperature. You'd feel your saliva bubbling on your tongue, your eyes swelling, your skin puffing up as the water in your tissues turned to vapor. You'd have about 15 seconds of useful consciousness. 15 seconds to realize the enormity of your situation, to understand that you're dying in the most alien way imaginable. Your blood wouldn't boil, thankfully, because your circulatory system provides enough pressure to prevent that. But you'd lose consciousness as the oxygen in your bloodstream depleted. Within 90 seconds, you'd be dead. And here's the truly terrifying part. This isn't some theoretical scenario involving exotic phenomena or rare cosmic events. This is just the baseline state of space. This is what space is like on a normal day. In a normal region, with nothing particularly unusual happening, the default condition of the universe is instantly lethal to human beings. But let's say you're smart about it. Let's say you're in a spacesuit, properly protected from the vacuum. You've solved one problem, but you've barely scratched the surface of what space has in store for you. Now you have to contend with temperature. And space's relationship with temperature is deeply unsettling. Space itself doesn't have a temperature in the way we usually think about it, because temperature is a measure of molecular motion, and space has essentially no molecules. But objects in space very much do have temperature, and the extremes are staggering. In direct sunlight, without an atmosphere to scatter and moderate the radiation, temperatures can soar to over 250 degrees Fahrenheit. Step into shadow, where the sun's rays can't reach you, and temperatures plummet to minus 250 degrees Fahrenheit or lower. That's a 500-degree temperature difference depending on whether you're in light or shadow. Your spacesuit has to somehow manage this, maintaining a livable temperature for your body, while the outside environment swings between extremes that would kill you in minutes. And it's not like Earth, where air and water currents distribute heat. In space, heat can only transfer through radiation and direct contact. There's no convection without air. This means heat management becomes an elaborate engineering challenge, one where failure means you either freeze solid or cook inside your own suit. Every spacewalk, every moment outside the protective shell of a spacecraft. It involves trusting that these thermal systems won't fail, that the delicate balance between heating and cooling will hold. And sometimes, it doesn't. Astronauts have reported water leaking into their helmets during spacewalks, a malfunction that could easily turn fatal if it interferes with breathing or vision. In space, there's no pulling over to the side of the road, no calling for immediate help. You're utterly dependent on your equipment functioning perfectly, constantly, without fail. Then there's radiation. And this is where space reveals itself to be not just passively hostile, but actively dangerous in ways that accumulate over time, invisibly destroying you at a cellular level. Earth's atmosphere and magnetic field protect us from the worst of the radiation streaming through space. We're surrounded by a protective bubble that deflects and absorbs charged particles from the sun, cosmic rays from distant supernova, and other forms of radiation that would otherwise make the surface of our planet uninhabitable. Step outside that protective bubble, and you're exposed to radiation levels that are genuinely frightening. Solar radiation is the most immediate concern. The sun constantly emits a stream of charged particles called the solar wind, and periodically it releases massive bursts of radiation called solar flares and coronal mass ejections. These events can release as much energy as billions of nuclear bombs, sending waves of deadly radiation streaming through the solar system. On Earth, we barely notice them, maybe seeing some spectacular auroras if we're lucky. In space, they can be lethal. A major solar event could deliver a radiation dose high enough to cause acute radiation sickness in a matter of hours. Astronauts on the International Space Station, which orbits within Earth's protective magnetosphere, have some shielding from these events. But future missions to the Moon or Mars will leave astronauts far more vulnerable. A solar storm during a Mars mission could expose astronauts to radiation levels equivalent to getting hundreds of chest X-rays, causing nausea, fatigue, and potentially long-term damage that could lead to cancer years or decades later. But solar radiation is just the beginning. Cosmic rays, high-energy particles traveling at nearly the speed of light from sources across the universe, constantly bombard anything in space. These particles are so energetic that they can punch straight through spacecraft hulls, through spacesuits, through human bodies. When a cosmic ray hits living tissue, it doesn't just damage the cells, it strikes directly. It creates a shower of secondary particles, spreading the damage in a cone of destruction through your body. Studies of astronauts who've spent extended time in space show increased rates of cataracts, cardiovascular disease, and cancer. The longer you spend in space, the more this radiation accumulates, invisibly shredding your DNA, increasing your risk of mutations and cellular damage that might not manifest for years. And here's something that keeps NASA scientists up at night. We don't fully understand the long-term effects of space radiation on the human body. We've never had humans spend years in deep space, outside Earth's magnetic field. The astronauts who went to the Moon were only exposed for a matter of days. Mars missions would take months or years. We're talking about exposing human beings to radiation environments we can't fully replicate on Earth, can't fully test for, can't fully predict. Every long-duration space mission is, in some sense, a medical experiment, with astronauts as the test subjects. They're accepting an increased lifetime risk of cancer that we can only estimate, not precisely calculate. That's not science fiction horror. That's the real cost of leaving Earth's protective embrace. Consider the isolation, the psychological dimension of space's terror. Humans evolved as social creatures, living in groups, surrounded by the familiar sights, sounds, and smells of Earth. We need social connection like we need food and water. Put a person in isolation, cut them off from normal human contact, and psychological problems emerge quickly. Depression, anxiety, cognitive decline, even hallucinations can develop. Now imagine that isolation taken to an almost incomprehensible extreme. You're not just isolated from friends and family, you're isolated from everything you've ever known. You're in a tiny metal box, surrounded by an infinite void that would kill you instantly if the walls failed. Everyone you love, every place you've ever been, every other human being who has ever existed, all of it is on a blue marble hanging in the darkness, getting smaller and smaller as you drift further away. The psychological strain of this kind of isolation is hard to overstate. On the International Space Station, astronauts can at least see Earth below them, a constant reminder that home is right there, just a few hundred miles away. But on a mission to Mars, Earth eventually becomes just another point of light in the sky, indistinguishable from the stars. You can't call home in real time. Communication delays stretch to 20 minutes or more each way. If something goes wrong, if you have a medical emergency or a psychological crisis, there's no one coming to help you. No rescue is possible. You are more alone than any human being has ever been in history. And this isn't theoretical. We've seen hints of the psychological toll space takes. Astronauts on long-duration missions report changes in their perception of time, difficulty sleeping, interpersonal conflicts with crewmates. These are highly trained, psychologically screened, emotionally stable individuals, and even they struggle with the mental demands of space. The confined spaces, the lack of privacy, the constant low-level stress of knowing you're surrounded by a lethal environment, it all accumulates. Arguments over trivial matters can escalate because there's nowhere to go to cool off. No way to escape the presence of people who might be getting on your nerves. The stress can manifest physically too, with reported cases of skin problems, digestive issues, and other stress-related ailments. Asterisk, then there's the effect space has on the human body itself. The way microgravity slowly dismantles the machinery of human physiology. We evolved under the constant pull of Earth's gravity. Our bones, muscles, cardiovascular system, even our sense of balance. All of it developed in response to gravity's steady tug. Remove that gravity, and the body begins to fall apart in disturbing ways. Bones lose density at an alarming rate, about 1 to 2% per month in space. That might not sound like much, but on a multi-year Mars mission, an astronaut could lose 20 or 30% of their bone mass in critical areas like the hips and spine. That's equivalent to decades of osteoporosis compressed into a few years. The bones become brittle, fragile, vulnerable to fractures. And unlike muscle, which can be rebuilt with exercise, bone loss is difficult to reverse even after returning to Earth. Asterisk muscles atrophy rapidly without gravity. To work against, even with rigorous daily exercise, astronauts lose muscle mass and strength. The heart, no longer needing to pump blood against gravity, becomes weaker and more spherical in shape. The spine lengthens as the vertebrae spread apart without gravity compressing them, causing many astronauts to grow an inch or two taller in space, often accompanied by severe back pain. Fluids shift upward in the body, causing faces to puff up and legs to thin out, giving astronauts a characteristic puffy-faced appearance. This fluid shift can increase pressure inside the skull, affecting vision. Some astronauts have developed problems with their eyesight that persist even after returning to Earth, a condition called spaceflight-associated neuroocular syndrome. The exact mechanism isn't fully understood, but it's thought that increased intracranial pressure damages the optic nerve and deforms the eyeball. Asterisk the immune system weakens in space. Viruses that lie dormant in the body, like the herpes virus, can reactivate. Wounds heal more slowly. Astronauts become more susceptible to infections. Even sleep becomes problematic, with many astronauts reporting difficulty sleeping and relying on sleep medication. The absence of natural day-night cycles, the constant hum of machinery, the knowledge that you're in a dangerous environment, all of it interferes with the body's natural rhythms. And perhaps most disturbing, recent studies have shown changes in gene expression in astronauts during the stress of the space environment actually alters how genes are turned on and off, with implications we're only beginning to understand. Most of these changes revert after returning to Earth, but some may be permanent. Asterisk all of this physical deterioration happens while you're also trying to conduct a mission, maintain equipment, make critical decisions. You're fighting your own body's decline while navigating an environment where a single mistake could be catastrophic. And the longer you stay in space, the worse it gets. The human body simply was not designed for this. We're Earth creatures, adapted to Earth's environment, and space is slowly, methodically breaking us down. Asterisk, let's talk about the mechanical side of surviving in space. The spacecraft and equipment we depend on utterly. Every single system on a spacecraft is a potential point of failure. And in space, failures can cascade rapidly from inconvenience to disaster. The spacecraft is simultaneously your shelter, your life support system, your transportation, and your only link to home. It has to provide breathable air, drinkable water, stable temperature, radiation, shielding, propulsion, navigation, communication, power, waste management, and countless other functions. Every one of these systems is complex, containing thousands of parts, each of which can malfunction. Asterisk take the air recycling system. For instance, on Earth, if your air conditioning breaks, you open a window. In space, the environmental control system is your lifeline. It scrubs carbon dioxide from the air, maintains oxygen levels, controls humidity, filters out contaminants. If it fails, you have hours at best before carbon dioxide levels rise to dangerous levels. You'd become confused, lethargic, eventually losing consciousness as the air you're breathing slowly poisons you. Spacecraft carry backup systems, redundancies, extra supplies, but everything in space has a limit. You can't just run to the store for more oxygen scrubbers. Asterisk water recycling systems are equally critical and disturbingly complex. On the International Space Station, water is so precious that urine and condensation are recycled into drinking water. The system works remarkably well, but it requires constant maintenance. Filters clog, pumps fail, contaminants build up. Astronauts spend a significant portion of their time just maintaining life support systems, fighting a constant battle against entropy and mechanical failure. And in deep space, far from Earth, there's no possibility of resupply. Every drop of water, every breath of air, has to be carefully managed and recycled. Run out, and you die. It's that simple. Asterisk power systems present their own set of terrifying failure modes. Most spacecraft rely on solar panels for power, but solar panels degrade over time from radiation exposure and micrometeorite impacts. On a long mission to Mars, panels will produce less and less power as they age, forcing difficult decisions about what systems to run and what to shut down. Some missions use nuclear power sources, which are more reliable but come with their own risks. The radioisotope thermoelectric generators used on deep space probes contain plutonium, generating power from radioactive decay. They're well shielded and incredibly reliable, but they're also permanent sources of radiation that can never be truly turned off. And if something goes wrong during launch, if the rocket explodes, you're potentially dispersing radioactive material into the atmosphere. It's a risk we accept because the alternatives are worse, because some missions simply can't function on solar power alone. Asterisk then, there's the problem of navigation and propulsion. In space, there are no landmarks, no GPS satellites beyond Earth orbit, no roads to follow. Navigation relies on precise tracking of star positions, communication with Earth-based tracking stations, and complex calculations of orbital mechanics. Get your navigation wrong, and you could miss your target entirely, drifting off into space with no way to correct course because you've exhausted your fuel. Propulsion systems have to work perfectly, firing at exactly the right time for exactly the right duration to adjust trajectory. Too little thrust and you miss your target. Too much and you might send yourself on an uncontrollable trajectory. The margins for error are razor thin. Asterisk and spacecraft are fragile in ways that aren't immediately obvious. The hull might seem solid, but it's actually quite thin. A delicate shell separating you from instant death. It has to be thin to save weight, because every pound of spacecraft requires exponentially more fuel to launch and maneuver. This thin skin is all that stands between you and the vacuum, and it's vulnerable to impacts. Space might seem empty, but it's actually filled with debris. Micrometeoroids, tiny specks of rock and metal traveling at tens of thousands of miles per hour, constantly bombard anything in space. Most are too small to cause serious damage, but larger ones can punch through spacecraft hulls, creating leaks or damaging critical systems. Around Earth, the problem is even worse because we've surrounded our planet with a cloud of space junk. Debris from decades of satellites, rocket stages, and other hardware. There are millions of pieces of debris in Earth orbit, ranging from tiny flecks of paint to dead satellites the size of buses. They're traveling at orbital velocities, which means even a small piece carries enormous kinetic energy. A paint fleck traveling at 17,000 miles per hour hits with the force of a bullet. Larger debris can be catastrophic. The International Space Station has been maneuvered multiple times to avoid debris on collision courses. Its modules are equipped with extra shielding, layers of material designed to break up incoming debris before it can penetrate the hull. But this protection is far from perfect. A large enough piece of debris, or one hitting at just the wrong angle, could tear through the station, creating a massive leak or destroying critical systems. And once a collision happens, it creates more debris, which can cause more collisions, potentially triggering a cascade effect called Kessler syndrome, where Earth orbit becomes so full of debris that satellites and spacecraft are constantly being destroyed, creating more debris in a runaway reaction that could make certain orbital regions unusable for generations. Every time astronauts go on a spacewalk, they're acutely aware that their suits and the station's hull have taken countless micrometeorite impacts. Most are too small to notice, but you can see the pockmarks and scars on equipment that's been in space for years. It's a constant reminder that space is not empty, that you're moving through a shooting gallery where the bullets are invisible and arrive without warning. Consider the sheer distance involved in space travel, and how those distances transform every problem into a potential death sentence. On Earth, if something goes wrong, help is usually minutes or hours away. Emergency services can reach almost anywhere on the planet within a day. In space, you're on your own, in ways that are hard to truly grasp. The International Space Station orbits just 250 miles above Earth's surface. That's barely the distance from New York to Washington, D.C., yet it's far enough that rescue becomes incredibly complicated. If something catastrophic happened on the ISS, it would take hours at minimum to prepare and launch a rescue mission, and days or weeks to actually reach the station, assuming a rescue vehicle is even available and ready. Now consider missions beyond Earth orbit. The Moon is about 250,000 miles away, a 3-day journey under normal circumstances. Mars, at its closest approach to Earth, is still around 35 million miles away, a trip that takes 6 to 9 months with current propulsion technology. At that distance, Earth is a pale blue dot, barely distinguishable from stars. The psychological impact of seeing your entire world reduced to a point of light cannot be overstated. But more practically, those distances mean that communication becomes frustratingly slow. Radio signals travel at the speed of light, which sounds fast until you're dealing with interplanetary distances. Earth to Mars communication has a delay of between 4 and 24 minutes one way, depending on the relative positions of the planets. That means a 48-minute wait for a response to any question or request for help in the worst case scenario. Imagine dealing with an emergency with that kind of communication delay. You can't have a real-time conversation with mission control. You can't get immediate advice or guidance. Every decision has to be made locally, by people who may be injured, stressed, running out of air, or dealing with failing systems. You send a message saying something's wrong, then you wait, knowing that by the time the response arrives, the situation may have changed completely. You may have already solved the problem or died trying. This communication delay fundamentally changes the nature of astronauts have to be far more autonomous, far more capable of handling problems independently, because there's no real-time support available. And if something goes truly wrong, if the spacecraft is damaged beyond repair, or crew members are seriously injured, there's no rescue possible. You can't send a rescue mission to Mars. By the time it arrived, months later, everyone would be long dead. The people on a Mars mission are accepting that if something goes catastrophically wrong, they're going to die. And there's nothing anyone on Earth can do about it except watch and listen as the communications grow more desperate and then finally stop. This has never happened, thankfully, but it's a very real possibility that every deep space mission has to confront. The astronauts know it, the mission planners know it, and it adds a layer of existential dread to every decision, every system check, every moment of the mission. Think about what it means that we've barely explored any of space, that the vast majority of the universe is not just unknown to us, but fundamentally unknowable with current technology. The furthest humans have ever traveled is to the moon, a journey of less than 250,000 miles. The International Space Station, humanity's furthest outpost, is only 250 miles up, so close to Earth that it's still within the planet's protective magnetosphere. In cosmic terms, we haven't left home at all. We've barely stepped off the front porch. The solar system is vast beyond intuitive comprehension. Light from the sun takes 8 minutes to reach Earth. It takes over 4 hours to reach Neptune, the furthest planet. To reach the edge of the solar system, the boundary where the sun's influence fades and interstellar space begins, light takes about 17 hours. Our fastest spacecraft, Voyager 1, launched in 1977 and is now beyond the solar system's edge, but it's been traveling for over 40 years and has covered less than a single light day of distance. The nearest star, Proxima Centauri, is over 4 light years away. With current technology, it would take tens of thousands of years to reach it. But the real terror comes when you expand your view beyond our immediate stellar neighborhood. Our galaxy, the Milky Way, contains hundreds of billions of stars and spans about 100,000 light-years across. It's so large that if you could travel at the speed of light, it would take you 100,000 years to cross from one side to the other. And the Milky Way is just one galaxy among billions in the observable universe. The distances between galaxies are even more staggering. The nearest large galaxy to us, Andromeda, is 2.5 million light-years away. The observable universe extends for about 93 billion light-years. These distances aren't just large. They represent fundamental limits to what we can ever know or experience. The speed of light isn't just fast, it's a cosmic speed limit, built into the fabric of space-time itself. Nothing can travel faster than light, and even reaching a significant fraction of light speed requires energy resources far beyond anything we can currently achieve. This means the vast majority of the universe is forever beyond our reach. We can observe distant galaxies, see them as they were billions of years ago when the light we're seeing today first left them, but we can never visit them, never learn what happened to them in the eons since that light began its journey to us. For all practical purposes, they exist in our past, unreachable, unknowable in their present state. This enforced isolation should be terrifying. We're trapped on a tiny rock orbiting an average star in an unremarkable region of a typical galaxy, and the universe has arranged itself so that we can never leave this small corner of it. We can look, but we can never touch, never explore, never know what wonders or horrors lie in the vast darkness beyond our light. Entire galactic civilizations could rise and fall in distant galaxies and we would never know, could never know, because the information can't reach us faster than light allows. Even within our own galaxy, the distances are prohibitive. If we somehow developed the technology to travel at 10% the speed of light, which would require revolutionary advances in propulsion, it would still take 40 years to reach Proxima Centauri. The travelers would be gone for most of their lives, and anyone left behind would have to wait decades for even a message saying they'd arrived safely. Interstellar travel isn't just technologically challenging, it's a commitment to severing almost all ties with home. 2. Accepting that everyone you know will age decades or die while you're in transit, that you may never see Earth again, that you're essentially emigrating to a new world with no real possibility of return. Now let's discuss some of the more exotic dangers lurking in space. The phenomena that sound like science fiction but are terrifyingly real. Black holes are perhaps the most famous, and for good reason. There are regions where gravity has become so intense that it's warped space-time itself into a point of no return. Cross the event horizon, the boundary around a black hole, and escape becomes impossible. Not just difficult, not just impractical, but physically impossible. The gravity is so strong that it bends the paths of all possible futures inward, toward the singularity at the center. You would be stretched and compressed by tidal forces, elongated like spaghetti in a process cheerfully termed spaghetti, pulled apart atom by atom as the difference in gravitational force between your head and feet exceeded the molecular bonds holding you together. But you don't have to fall into a black hole for it to affect you. The gravity around a black hole is so intense that it slows time itself. Get close enough, and time dilation becomes extreme. An observer watching you approach a black hole would see you slow down, your movements becoming more and more sluggish as you neared the event horizon, until you appeared to freeze entirely. Your image lingering at the edge forever, redshifted and fading. From your perspective, you'd fall through normally, but the rest of the universe would appear to speed up. Stars dying and being born in rapid succession, time itself running away from you. You could fall into a black hole and, from a certain perspective, never quite arrive. Frozen at the threshold for eternity, while simultaneously being destroyed from your own point of view. The universe contains millions of black holes, remnants of massive stars that exhausted their fuel and collapsed under their own gravity. Stellar mass black holes are perhaps 10 to 50 times the mass of our sun, compressed into a region a few miles across. But at the centers of most galaxies, including our own, lurk supermassive black holes. Millions or billions of times more massive than the sun. The black hole at the center of our galaxy, Sagittarius A*, is about 4 million times the sun's mass. We're in no danger from it. We're about 26,000 light-years away and orbiting safely. But its mere existence is unsettling. It's a cosmic predator sitting at the heart of our galaxy, feeding on any matter that strays too close. Neutron. Stars are similarly terrifying. The collapsed core of dead stars compress two densities that defy comprehension. A neutron star packs more mass than the sun into a sphere only about 12 miles across. A teaspoon of neutron star material would weigh about 1 billion tons. The surface gravity is so intense that if you dropped an object from just 1 meter above the surface, it would hit with more kinetic energy than a nuclear bomb. The gravitational field is strong enough to bend light rays, allowing you to theoretically see the backside of the star by looking forward as the light curves around it. Some neutron stars are pulsars, spinning at incredible rates and beaming radiation from their magnetic poles. As they spin, these beams sweep across space like cosmic lighthouses. Some pulsars rotate hundreds of times per second. The fastest known pulsar spins 716 times per second. That's a 12-mile wide sphere of ultra-dense matter, spinning fast, enough that its equator is moving at a significant fraction of the speed of light. The magnetic fields around pulsars are the strongest in the universe. Trillions of times stronger than Earth's magnetic field, powerful enough to disrupt the atomic structure of matter and rip apart molecules. If you got anywhere near a pulsar, the magnetic field would interfere with the electrical signals in your nervous system. The radiation would cook you, and the gravity would tear you apart. Then there are magnetars, a special type of neutron star with magnetic fields thousands of times stronger than regular pulsars. A magnetar's magnetic field is so intense that it warps the shape of atoms themselves, stretching them into elongated needles. These fields are powerful enough to be lethal at a distance of over 600 miles. The magnetic field alone, not the radiation, not the gravity, just the raw magnetic force, would kill you by disrupting the electromagnetic forces that hold your atoms together. Magnetars occasionally have starquakes, sudden shifts in their crusts that release tremendous amounts of energy in the form of gamma rays and X-rays. In 2004, a magnetar about 50,000 light-years away had a flare that affected Earth's ionosphere. Despite being halfway across the galaxy, the burst of radiation, traveling for 50,000 years across space, was still powerful enough when it arrived to measurably impact our planet's upper atmosphere. Gamma ray bursts are perhaps the most destructive events in the universe, and we're not entirely sure what causes all of them. Some appear to be produced when massive stars collapse into black holes, others when neutron stars collide. For a brief period, seconds, 2 minutes, a gamma ray burst can outshine the entire rest of the universe in gamma rays, releasing in that short times as much energy as the sun will produce over its entire 10 billion year lifetime. These are jets of intense radiation, beamed out in specific directions. If you happen to be in the path of one, even from hundreds or thousands of light years away, the radiation dose would be catastrophic, stripping away planetary atmospheres, destroying the ozone layer, bathing the surface in lethal radiation. There's speculation that gamma ray bursts may have caused mass extinctions on Earth in the past. We can't see them coming. There's no warning. Gamma rays travel at the speed of light, so the first sign that a gamma ray burst is heading your way is when it arrives and starts sterilizing your planet. And there's nothing you can do about it. No shielding would be adequate against that level of radiation. Your only hope would be that you're not in the beam's path, that the cosmic lottery spares you. It's one of the ways the universe could snuff out life on Earth without warning, without malice, simply as a byproduct of stellar physics playing out on a scale we can barely comprehend. Space is also filled with more subtle dangers, phenomena we're only beginning to understand. Dark matter makes up most of the matter in the universe, but we can't see it, can only detect its presence through its gravitational effects. We don't know what it is, what it's made of, how it behaves. It passes through normal matter, through planets and stars, and us, constantly, without interaction. For all we know, the space your body occupies right now contains a significant density of dark matter, particles streaming through you every second, and we simply can't detect them. The universe is made mostly of something we don't understand, and that should be deeply unsettling. Dark energy is even more mysterious. It's causing the expansion of the universe to accelerate, pushing galaxies apart at ever-increasing rates. We call it dark energy because we don't know what it is, but we can measure its effects. It makes up about 70% of all the energy in the universe. That means the universe is dominated by a phenomenon we don't understand, a force that's pushing everything apart, and we don't know why it exists or what its long-term implications are. Some theories suggest that dark energy could eventually rip apart galaxies, solar systems, planets, atoms themselves in a scenario called the Big Rip, or it might be stable, continuing to push the universe apart until everything is cold, dark, and infinitely separated. Either way, the universe's fate is in the hands of something we can't see, can't understand, and can't control. Asterisk, let's bring this back to something more immediate. The very real dangers that space poses to any human settlement beyond Earth. Imagine we establish a base on the Moon or Mars. These would be humanity's first permanent settlements beyond Earth, and they would be unimaginably fragile. Every resource has to be imported from Earth or manufactured locally using limited materials and equipment. Food, water, air, spare parts, medicine, everything has to be carefully managed. Supply runs from Earth would take days for the Moon, months for Mars, and cost enormous amounts of money and resources. A settlement would have to be largely self-sufficient, but self-sufficiency requires a robust industrial base, skilled workers, redundant systems. Asterisk A. Single disaster, a fire, a major equipment failure, a crop disease, wiping out food supplies. Any of these could doom the entire settlement. On Earth, if a town burns down, survivors can flee to neighboring communities, rebuild with help from outside. On the Moon or Mars, there is no neighboring community. There's no breathable air to escape into, no wild plants to forage, no water to drink except what you've already processed and stored. A settlement would be a tiny bubble of life in an utterly dead world, and any breach of that bubble would be catastrophic. Asterisk, the settlers would live with constant awareness of their vulnerability, knowing that they depend on systems that cannot fail, on supply lines that cannot break, on equipment that must continue functioning because there's no replacement available and won't be for months or years. The psychological toll of this would be immense. Studies of isolated communities like Antarctic research stations show increased rates of depression, interpersonal conflict, and psychological stress, and those communities can at least be evacuated in emergencies, can receive new supplies regularly, can communicate with the outside world in real time. A Mars settlement would be more isolated than any human community has ever been. And then there's the problem of governance and social stability. A space settlement would need rules, laws, systems for resolving disputes. But who makes those rules? Who enforces them? On Earth, we have the luxury of complex governmental and legal systems backed by the ability to enforce decisions through various means. In a small, isolated settlement where everyone depends on everyone else for survival, traditional systems of governance might not work. One person refusing to do their job, one conflict escalating out of control, could threaten the entire community. There would be no police to call, no courts to appeal to, no higher authority except perhaps Earth, which is too far away to intervene in time. Asterisk, the potential for things to go wrong in social dynamics is staggering. Small groups in isolation often develop internal conflicts, form factions, struggle with leadership issues. Add the stress of living in a hostile environment where everyone's survival depends on perfect cooperation, and the pressure becomes almost unbearable. History is full of examples of isolated settlements falling apart due to internal strife. And those settlements were on Earth, with air and water and food potentially available if they could just work things out. A space settlement has no such margin for error. Social collapse means everyone dies. Asterisk, consider also the ethical implications of space settlement, particularly the question of children. Should children be born in space, raised in these fragile, dangerous environments? Some would argue that establishing a multiplanetary civilization requires it. That permanent settlement means families, reproduction, the continuation of the species beyond Earth. But imagine growing up on Mars, knowing that the world outside, your habitat is instantly lethal, that you can never go outside without a spacesuit, never feel rain on your skin, or breathe fresh air, or see a blue sky. You'd grow up in a cramped, artificial environment, entirely dependent on technology, always aware that equipment failure means death. Asterisk, and there are physical concerns too. Children born in low-gravity environments like Mars, which has about 1/3 Earth's gravity, would develop differently. Their bones and muscles would adapt to the local gravity, which might make them stronger and healthier in that environment, but also might mean they could never visit Earth without severe health problems. The stress of Earth's gravity might be too much for a body that developed on Mars. The cardiovascular system unable to cope with pumping blood against that much gravitational force. A child born on Mars might be trapped there forever, physically incapable of visiting the world there. Parents came from, they would be, in a very real sense, a new branch of humanity, adapted to an alien world, separated from Earth by more than just distance. Asterisk, there's also the question of what we might find in space. What might be waiting out there in the darkness that we haven't yet encountered? The universe is vast enough that even statistically improbable things become almost certain given enough space and time. We've found none, but the universe has had billions of years to develop life, intelligence, and possibly civilizations, far more advanced than ours. The famous Fermi paradox asks, if intelligent life is common in the universe, where is everyone? Why haven't we detected any signs of alien civilizations? Asterisk, the possible answers to this question range from hopeful to terrifying. Maybe intelligent life is extremely rare, and we're alone in the universe, which is its own kind of cosmic horror. The idea that in all the vastness of space, on all the billions of planets orbiting billions of stars, in billions of galaxies, we're the only ones conscious enough to ask the question. That would make us incredibly special, but also incredibly isolated. Forever alone, in a universe too large to ever fully explore. Asterisk, or perhaps intelligent, life is common, but something prevents civilizations from becoming detectable. This is where the truly frightening possibilities emerge. Maybe there's a great filter, some challenge or danger that wipes out civilizations before they can spread across the stars. Maybe it's nuclear war, climate catastrophe, artificial intelligence, gone wrong, or some threat we haven't even imagined yet. And the terrifying question is the great filter behind us or ahead of us? Did we already pass through the unlikely step? Perhaps the emergence of complex life or intelligence, meaning we're through the worst of it? Or is it waiting for us in the future, some inevitable disaster that befalls every technological civilization, right around the time they develop the ability to destroy themselves? Asterisk, some theorists have proposed even darker possibilities. Perhaps advanced civilizations exist, but deliberately hide from younger species like us. Why would they hide? Maybe because the universe is a dangerous place where revealing your presence is a death sentence? This is the dark forest hypothesis, named after a science fiction novel but taken seriously by some scientists. The idea is that the universe is like a dark forest where every civilization is a hunter, staying silent and hidden, because announcing your presence might attract the attention of others who see you as a threat to be eliminated. In this scenario, the reason we haven't heard from anyone is that everyone is hiding, and the moment we broadcast our presence too loudly, we might attract something we really don't want to meet. Asterisk, it sounds paranoid, but consider it from a game theory perspective. An advanced civilization encountering another species faces a prisoner's dilemma. They don't know if the other species is friendly or hostile, peaceful or aggressive. They don't know if the other species will become a threat in the future. The safest move, in pure survival terms, is to strike first, to eliminate potential threats before they can become actual threats. This logic applies at every level of technological development, meaning any species that survives long enough to become spacefaring might have done so by being ruthlessly cautious about contact with, but there's asterisk. We've already been broadcasting our presence to the universe for over a century, since we started using radio transmissions. Those signals are spreading outward at the speed of light, a growing sphere of electromagnetic noise that marks our location to anyone who might be listening. We've even deliberately sent messages to the stars, like the Arecibo message broadcast in 1974, containing information about Earth, humanity, and our solar system. If there's something hostile out there, something with capabilities beyond our comprehension, we might have already rung the dinner bell, and we'd never see it coming. Any civilization advanced enough to travel between stars would have technology that would seem like magic to us. They could be observing us right now, and we'd never know. They could be heading our way, and we wouldn't detect them until they arrived. Asterisk, this is speculative, of course. But the universe's silence is genuinely puzzling and potentially disturbing. We've been searching for signals from extraterrestrial intelligence for decades with increasingly sophisticated equipment, scanning thousands of stars, and we've found nothing. The universe seems to be eerily quiet. That silence might simply mean we're alone or that civilizations are rare and far apart. But it might mean something more sinister, that there's a reason no one is talking. That survival in the cosmos requires silence. Asterisk, even if we never encounter hostile aliens. The universe contains threats that could end human civilization without warning. Asteroids and comets constantly rain down on the inner solar system. Most are small and burn up in Earth's atmosphere as meteors. But larger ones make it through, and the largest can cause global catastrophes. 66 million years ago, an asteroid about 6 miles in diameter struck the Earth near what is now the Yucatan Peninsula. The impact released energy equivalent to billions of nuclear bombs, triggering earthquakes, tsunamis, and volcanic eruptions. Debris thrown into the atmosphere blocked out the sun for months or years, causing global cooling and the collapse of food chains. The dinosaurs, which had ruled Earth for over 160 million years, were wiped out, along with about 75% of all species on the planet. Asterisk, that was not a unique event. Earth's surface is scarred with impact craters, evidence of countless collisions over its history. Smaller impacts have caused regional devastation, like the Tunguska event in 1908, when an asteroid or comet fragment exploded over Siberia with the force of a large nuclear weapon, flattening trees for miles around. If that had happened over a populated area, it would have killed thousands. An ocean impact could generate tsunamis that would devastate coastlines around the world. A large enough impact could end human civilization, killing billions directly, and causing a collapse of agriculture and infrastructure that would doom most survivors. We're actively tracking near-Earth asteroids now, cataloging objects that might pose a threat, but our survey is far from complete. There are thousands of asteroids large enough to cause serious damage that we haven't found yet. And comets are even more concerning because they spend most of their time in the outer solar system, only becoming visible when they fall inward toward the sun. A large comet on a collision course with Earth might give us only months or weeks of warning. Nowhere near enough time to mount a serious deflection effort with current technology. Asterisk, the universe doesn't care about humanity's survival. It's not hostile, but it's not friendly either. It's indifferent, operating according to physical laws that have no regard for life or consciousness or the continuation of any particular species. Asteroids don't target planets. They simply follow their orbits according to gravity's dictates, and sometimes those orbits intersect with Earth's. Stars go supernova not because they intend harm, but because they've exhausted their fuel and the physics of stellar evolution demands collapse and explosion. Gamma ray bursts aren't aimed. They're just jets of energy, released during cosmic catastrophes, and if one happens to point at Earth, well, that's just bad luck. Asterisk, this indifference is in some ways more frightening than active hostility. You can fight an enemy, devise strategies, mount defenses, but how do you fight the fundamental nature of reality? How do you defend against the universe simply being what it is, vast and violent, and operating on scales where human life is less than a rounding error? We exist in a narrow band of conditions, requiring specific temperatures, pressures, chemical compositions, radiation levels. Step outside that band in any direction, and we die. The universe is almost entirely outside that band. The vast majority of space is vacuum and radiation. The vast majority of matter is inside, stars being fusion processed, or locked in planets with crushing gravity, or toxic atmospheres, or frozen in the depths of space. The conditions that allow for human life are vanishingly rare, temporary, fragile, asterisks, and those conditions are not stable. Earth itself has been through periods that would have been uninhabitable for humans. Snowball Earth events where the planet froze over almost entirely. Hothouse periods with no polar ice and much higher temperatures. The composition of our atmosphere has changed dramatically over geological time, from an early atmosphere with almost no oxygen to the oxygen-rich atmosphere we breathe today, a change caused by photosynthetic organisms that poised the atmosphere with oxygen, a waste product that happened to be useful for new forms of life. The stable, comfortable climate we've enjoyed for the past 10,000 years is an anomaly. A brief warm period between ice ages, even without human-caused climate change, Earth's climate would eventually shift dramatically, as it always has. Asterisk, the sun itself is slowly growing brighter as it ages, a natural consequence of stellar evolution. In about 1 billion years, the sun will be bright enough that Earth's oceans will begin to evaporate, creating a runaway greenhouse effect that will turn Earth into something like Venus, with surface temperatures hot enough to melt lead. A long time away, but it's coming. Inevitably, driven by the physics of how stars work, in about 5 billion years, the sun will exhaust the hydrogen in its core and expand into a red giant, possibly engulfing Earth entirely, certainly rendering it uninhabitable. The sun that gives us light and life will eventually be our death sentence. Asterisk, even if we survive that long as a species, even if we've spread 2 other star systems by then, we face the ultimate fate of the universe itself. The universe is expanding, and that expansion is accelerating. Galaxies are moving apart, and eventually they'll move so far apart that they're no longer visible to each other. Each galaxy isolated in its own patch of space, surrounded by darkness. Stars will continue to form for many trillions of years. But eventually, the supply of hydrogen gas will be exhausted, and no new stars will be born. Existing stars will die, one by one, until the last star flickers out and the universe enters the era of black holes. Asterisk, black holes will slowly evaporate through Hawking radiation over timescales that make the current age of the universe seem like an eye blink. After something like 10 to the 100 years, even black holes will have evaporated, leaving nothing but a thin soup of fundamental particles, spread across an ever-expanding universe, growing colder and more dilute without end. This is heat death, the ultimate fate of the universe, according to our current understanding of physics. Everything that exists, every star and planet, every structure and form, every thought and feeling, all of it will eventually decay into maximum entropy, a state of perfect meaningless equilibrium. Asterisk, that's the endgame. The ultimate terror that space reveals when you follow the implications far enough. Everything ends. Not just individual lives or civilizations, but everything. The universe itself is marching toward a state where nothing of interest can happen, where complexity becomes impossible, where the very concept of structure or pattern ceases to have meaning, and there's nothing we can do about it. We can't reverse entropy, can't prevent the universe's expansion, can't rewrite the fundamental laws of physics that doom everything to eventual oblivion. Asterisk. But let's come back to more immediate terrors, the ones that face any actual space missions we might undertake in the near future. Consider the psychological impact of a journey to Mars, which would be humanity's most ambitious crewed mission. If we attempt it, you'd be confined in a spacecraft not much larger than a small house for 6 to 9 months, traveling through the void with a small group of people you'd better hope you get along with, because there's no leaving, no taking a break, no privacy beyond what you can find in a sleeping bag. Every day you'd wake up and look out the window to see nothing but darkness and distant points of light. Earth would shrink from a globe to a dot to just another star in the sky. Asterisk, you'd be bombarded by radiation the entire journey. Invisible particles, tearing through your body, damaging your cells in ways that might cause cancer years later. You'd exercise for hours each day to fight the muscle atrophy and bone loss, but it wouldn't be enough. You'd still arrive at Mars weaker than when you left. Your immune system would be suppressed, your vision potentially damaged, your body clock disrupted by the absence of natural day-night cycles. You'd be constantly aware that you're traveling through an environment that's trying to kill you, that only the thin walls of the spacecraft and the functioning of complex life support systems stand between you and death. Asterisk, and then you'd arrive at Mars, and the mission would really begin. Landing on Mars is notoriously difficult. The atmosphere is thick enough to require heat shields but too thin for parachutes to work effectively without additional braking. Spacecraft have to use retro rockets to slow down, burning fuel that adds weight, complicating the whole mission. The surface is strewn with rocks and slopes and potential hazards. Multiple missions to Mars have failed during landing, crashing, or losing contact at the crucial moment. When humans attempt it, that won't be a mission failure. It will be people dying, slamming into the surface at hundreds of miles per hour, or tipping over on landing and breaching their habitat, or any of a dozen other failure modes that mean death. Asterisk, assuming you survive landing, you'd be on Mars for at least a year and a half, waiting for the planets to align properly for the return journey. You'd live in a habitat that would make Antarctic research stations look spacious and luxurious by comparison. Probably a prefabricated structure landed ahead of time, with just enough room for the crew to live and work. You'd go outside, only in spacesuits dealing with Martian dust that's incredibly fine and sharp, getting into every seal and joint, potentially toxic if inhaled, a constant maintenance headache. The dust is also charged with static electricity, making it cling to everything. Asterisk, the Martian day is about 40 minutes longer than Earth's, which sounds minor but is enough to disrupt human circadian rhythms over time. Studies of people living on Mars time for rover missions show increased fatigue and cognitive issues. You'd be dealing with that while also managing a habitat, conducting research, maintaining equipment, growing food, processing water, all the tasks necessary to stay alive. One major equipment failure, one habitat breach, one serious injury or illness, and you might not make it to the return window. Asterisk, and then there's the return journey. Another 6 to 9 months in the cramped spacecraft, even weaker than before, because Mars's lower gravity would have allowed further bone and muscle loss. You'd be traveling with recycled air that's been recycled hundreds of times, water that used to be urine and sweat, food supplies that are dwindling and might not last if the journey takes longer than expected. You'd know that the spacecraft has been sitting in space for over 2 years, exposed to radiation and temperature extremes and micrometeorite impacts, and you'd have to trust that it's still functional enough to get you home. When you finally approached Earth, you'd have to hit the atmosphere at just the right angle. Too steep and you'd burn up from excessive heating. Too shallow and you'd skip off the atmosphere back into space. Threading that needle after months in space with degraded equipment and an exhausted crew, knowing that this is the only chance you'll get, would be terrifying. And even if everything goes perfectly, you'd land after being gone for 2.5 to 3 years, much of which was spent in reduced gravity. You'd be so weak that you might not be able to stand, needing months of rehabilitation to regain bone density and muscle strength. Some effects might be permanent. Your increased cancer risk from radiation exposure would follow you the rest of your life. Asterisk all of this for a mission to our nearest planetary neighbor. A world that's practically in our backyard by cosmic standards. Missions beyond Mars, to the outer planets or their moons, would be far more difficult. Jupiter and Saturn have intense radiation belts that would require heavy shielding. They're large moons, potentially interesting targets for exploration, because some might have subsurface oceans that could harbor life, orbit within these radiation belts. A crewed mission to Europa or in Protus would expose astronauts to radiation doses that might be lethal despite shielding. Asterisk, the outer solar system is also incredibly cold and dark. At Jupiter's distance from the Sun, sunlight is 27 times weaker than at Earth. At Saturn, 90 times weaker. At Neptune, 900 times weaker. Solar panels become increasingly impracticable. Temperatures plummet to hundreds of degrees below zero. The journey times stretch 2 years or decades with current propulsion. These are not places humans can easily visit. We can send robots, hardy machines that don't need air or warmth or radiation protection beyond what's needed to keep electronics functioning. But human exploration of the outer solar system is barely imaginable with foreseeable technology. Asterisk, interstellar travel is even more daunting. The distances are so vast that conventional rockets are essentially useless, even traveling at 10% the speed of light, which would require breakthrough propulsion technology we don't currently have. It would take over 40 years to reach the nearest star system. The crew would either need to survive for decades, aging through the journey, or we'd need some form of suspended animation or generation ships where multiple generations are born and die during the voyage. Generation ships present their own nightmare scenarios. Imagine being born on a spacecraft, raised knowing that you'll spend your entire life traveling through the void, never seeing the destination your grandparents left for or the world your grandchildren might reach. Your whole existence would be the ship, a tiny bubble of life in infinite darkness, traveling for decades or centuries toward a destination that might not even be habitable. When you arrive, asterisk, and what if something goes wrong? What if the ship's systems fail, or the target star turns out to have no suitable planets, or the society on board collapses into conflict? There's no turning back. There's no rescue. A generation ship would be completely cut off from Earth, communications taking years to cross the distances involved. The people on board would be truly alone, more alone than any humans have ever been, dependent entirely on the ship functioning properly for generations. One major systems failure, one critical part breaking without a replacement, and everyone dies, slowly, as life support fails or food supplies run out or any of the 1,000 things that keep people alive stop working. Asterisk, the engineering challenges of building a generation ship that can function reliably for centuries are staggering. Nothing humans have built has ever needed to function for that long without major maintenance and parts replacement. Even our most durable structures, ancient buildings and monuments, have required constant upkeep to remain standing. A generation ship would need to be completely self-sufficient, carrying the raw materials and industrial capacity to manufacture any part that might fail. It would need to recycle everything perfectly, because there's no resupply. Any loss of air or water or essential elements would compound over time until the systems failed. Asterisks, the social engineering is equally challenging. How do you ensure that a society confined to a spacecraft remains stable and functional for generations? How do you prevent knowledge loss? Ensure that future generations understand the ship's systems and can maintain them. How do you keep people motivated to continue a journey started by their ancestors for destinations they'll never see? History suggests this would be incredibly difficult. Isolated communities often develop their own cultures that diverge from the parent society, sometimes drastically. A generation ship's culture might evolve in ways that would make them alien to the humans who sent them. And if that evolution included forgetting how to maintain critical systems, the mission would end in disaster. Asterisk, space also confronts us with existential questions about human identity and purpose. If we do spread to other worlds, establish settlements on Mars or the moons of Jupiter, build habitats in the asteroid belt, or eventually reach other star systems, the humans living in those places will diverge from those on Earth. Different gravity, different radiation exposure, different selection pressures, possibly different genetic engineering choices. If we start modifying ourselves to better suit alien environments, give it enough time, thousands or millions of years, and these populations might diverge into separate species. Unable to interbreed with Earth humans, perhaps barely recognizable as human at all. Asterisk, this is evolution in action. Adaptation to new environments, and it means that the long-term future of humanity in space might not include anything we'd call human. Our descendants might be biological, or they might upload themselves into machines, or merge with artificial intelligence, or pursue forms we can't imagine. The drive to survive and spread across the universe might require becoming something other than human, abandoning our biological heritage for forms better suited to the harsh environments of space. And that raises deep questions about what we're trying to preserve, what we're trying to spread. Is it human DNA? Human culture? Human consciousness? If our descendants are so changed that they bear no resemblance to us, have we succeeded in spreading humanity, or just created something new that replaced us? Space is ultimately a mirror that reflects our deepest fears and limitations back at us. It shows us how fragile we are, how dependent on our specific environment, how unprepared for the reality beyond our atmosphere. It demonstrates the vast scales of time and distance that dwarf human concerns. That put our entire species' existence into cosmic perspective as a brief flicker. It reminds us that the universe doesn't care about our survival, that we exist in a narrow band of conditions that are temporary and exceptional rather than normal. The silence of space. The absence of any detected alien civilizations, the sheer hostility of the environment, the distances that trap us in our corner of the universe, all of it combines to create a pervasive sense of cosmic horror. We're alone in a hostile universe, or if we're not alone, that might be even worse. We're confined to a tiny planet that will eventually become uninhabitable, orbiting a star that will eventually die. In a universe that's marching inextricably toward heat death. Every mission beyond Earth is a desperate gamble against impossible odds. Every human in space is one malfunction away from death. Every future settlement is one disaster away from extinction. And yet, we keep looking up. We keep building rockets, training astronauts, planning missions. There's something in human nature that refuses to accept limitations, that sees the hostile void of space and thinks not of the dangers, but of the possibilities. We're terrified of space, rightfully so, because it can kill us in more ways than we can count. But we're also drawn to it, compelled by curiosity and ambition, and the simple fact that it's there, unknown and unexplored. The terror and the wonder are inseparable, two sides of the same coin. Space is genuinely terrifying because it's the ultimate test of human capability and will. It's an environment that wants to kill us, in a universe that's indifferent to whether we survive. Every moment spent beyond Earth's protection is a moment where we're fighting against the fundamental nature of reality itself, trying to carve out tiny bubbles of survivability in an ocean of death. The odds are against us, the distances are too vast, the dangers too numerous, the universe too hostile. And maybe that's why we keep trying. Because the terror of space is matched by the terror of never trying, of accepting our limitations, of staying confined to one world when an entire universe lies beyond our reach, no matter how hostile it might be. In the end, space terrifies us because it shows us the truth about our place in the cosmos. We're not the center of anything. We're not special. We're a species of clever apes on a small planet, barely beginning to venture beyond our cradle. Confronted with the reality that the universe is vast, and we are tiny, that we exist by accident in a narrow zone of habitability, that everything we build will one day crumble, that everyone we love will die, that our entire civilization is a brief moment in cosmic time, and that ultimately, nothing we do matters on a universal scale. The universe will continue long after humanity is gone, expanding and cooling and marching toward its inevitable end, utterly unconcerned with our brief existence. That's the ultimate terror that space reveals. Our cosmic insignificance, our mortality writ large, our impermanence made manifest in the eternal darkness between the stars.